Right now, as you sit there listening to me, the image on the back of your eyeball is upside down, completely inverted. The sky is at the bottom. The floor is at the top. Your feet are above your head. Every person, every tree, every building you have ever looked at in your entire life has landed on your retina flipped, reversed. You have never once had a right-side-up image in your eye. Not once, not for a single fraction of a second. Now most people, when they hear that, they say, oh sure, but the brain flips it back. And everybody nods like that explains everything. The brain flips it. Problem solved. Move on, next question. That explanation is completely wrong, and I want to show you why. Because the real answer tells you something much deeper about what it means to see. Something that should, if you really let it sink in, change the way you think about every visual experience you have ever had. Let's start with the easy part. Why is the image inverted in the first place? This is straightforward optics. Nothing controversial. Your eye has a lens. It sits right behind the cornea, near the front. And a converging lens, any converging lens, inverts images. That's just what lenses do. Light from above the center line gets bent downward. Light from below gets bent upward. Light from the left crosses over to the right. It's the same thing that happens in a pinhole camera, actually. You take a box, poke a tiny hole in one side, and the image that forms on the back wall is upside down. The lens in your eye is doing essentially the same thing, but more efficiently because it gathers more light. You can see this for yourself. Get a magnifying glass and a white piece of paper. Go into a dark room. Hold the magnifying glass between a window and the paper. Move the paper back and forth until the image of the window comes into focus. It will be inverted, upside down and left-right reversed. That image on the paper is exactly analogous to the image on your retina. The physics is identical, so we've got an upside-down image on the retina. Nobody disputes this. It's been known for centuries. Johannes Kepler figured it out back in 1604. He even found it disturbing. He couldn't quite work out how we see things right side up when the retinal image is inverted. And the answer that eventually became popular, the one everybody still repeats, is that the brain simply flips it. And here's where the trouble starts. Think about what the brain flips it actually means. It means there's some process inside your head that takes the upside-down picture and rotates it 180 degrees like you'd turn a photograph around in your hands. But who is looking at the picture before it gets rotated? And who is looking after? You see, if there's a picture that needs to be viewed, there has to be a viewer. Some little entity inside your skull, examining the image. The philosophers call this the homunculus, the little man. And the problem is obvious. If the little man is looking at the retinal image, then the little man has eyes too, and the images in his eyes are also upside down. So now you need an even smaller man inside his head to flip those images. And that smaller man needs an even smaller man, and so on forever. It's an infinite regress, a logical dead end. It doesn't explain anything. It just pushes the mystery back one step and pretends that counts as solving it. So let's throw out the brain flips it and actually ask what happens. The retinal image forms on a surface packed with photoreceptor cells. About 130 million of them. There are two types. Rods, which are sensitive to dim light but don't see color, and cones, which need more light but can distinguish wavelengths, which is how you get color vision. Now here is the crucial point. These photoreceptors do not pass a picture to the brain. Each photoreceptor individually absorbs photons and converts the energy into an electrochemical signal, a little pulse of voltage. That's all. One cell, one signal. The image as an image is destroyed at the retina. It's decomposed, shattered into 130 million independent electrical messages. Let me give you an analogy. Imagine you have a beautiful painting, a masterpiece. Now imagine you hire 130 million people, and each person is assigned to one tiny dot on the painting. Each person looks at their dot and writes down a single number describing how bright it is and what color it seems. Then you collect all 130 million slips of paper and throw the painting away. What you have now is not a painting, it's data. It's a massive pile of numbers. The painting is gone. You cannot ask whether the pile of numbers is upside down. The question has no meaning. Numbers don't have an orientation. That is exactly what happens in your eye. The image is converted into signals. And signals are not images. By the time any information leaves the retina and travels down the optic nerve, There is nothing to flip. There's no picture. There's no orientation. There is only a code. And this isn't just my interpretation. If you were to somehow tap into the optic nerve with an electrode and record the signals passing through, you would not find anything resembling an image. You'd find a stream of electrical pulses, spikes of voltage, firing at various rates in various patterns. It would look on an oscilloscope like noise. Structured noise, yes. Meaningful noise. Absolutely. But not a picture. The translation from image to code is complete and irreversible by the time the information leaves the eye. And by the way, the retina is already doing some processing before it even sends the signals along. It's not just passively capturing photons. There are layers of neurons right there in the retina itself, ganglion cells and bipolar cells and horizontal cells and amacrine cells that are already analyzing the data. They're enhancing contrast, they're detecting edges, they're responding to changes in light more than to absolute light levels because changes are usually more important than static brightness. The retina is, in a sense, an outpost of the brain. It grew from the same neural tube during embryonic development. It is brain tissue, sitting in your eyeball, doing brain-like work before any signal reaches your skull. So by the time the optic nerve carries its messages to the brain, what arrives is not a raw feed from a camera. It's already been pre-processed, filtered, edited. The retina has already decided what's interesting and what isn't, what deserves a strong signal and what can be attenuated. The image, whatever it was, is long gone. Now the brain receives this code, and what does it do? Does it reconstruct the image and look at it? No. There's nobody in there to look at it. What the brain does is something much more remarkable. It uses the code to build a model, a three-dimensional, full-color, continuously updated, predictive model of the world around you. And this model isn't like a photograph, it's more like a hypothesis. The brain's best guess about what's out there, based on the data it's receiving right now, combined with everything it has learned from a lifetime of experience. And this model is extraordinary, but it's also full of tricks and shortcuts and, frankly, lies. Let me show you what I mean. You think you see the world in high definition, sharp from edge to edge. You don't. The part of your retina that actually has sharp, detailed vision is a tiny region called the fovea. It's about 1.5 millimeters across. That's roughly the size of the head of a pin. The fovea covers maybe 2 degrees of your visual field. Hold your thumb out at arm's length. Your thumbnail. That's about the area of sharp focus. Everything else, everything outside that thumbnail is blurry. Terribly, embarrassingly blurry. If you could somehow freeze your eye in place and look at the world without moving it, you'd be shocked at how little you can actually resolve. But your eyes don't stay still. They're constantly jumping, 3 or 4 times a second in quick darting movements called saccades. Each saccade repositions the fovea onto a new point of interest. And your brain takes all those tiny, sharp snapshots and stitches them together seamlessly into what feels like a continuous, high-resolution panorama. But it's a fabrication. A magnificent fabrication, but a fabrication nonetheless. The brain is showing you a world that's sharper and more complete than what your eyes actually deliver. And here is something even sneakier. During each saccade, while your eyes are in the middle of jumping from one point to another, you are essentially blind. The image on your retina is a blurred smear during the jump, which would be very distracting if you perceived it. So your brain simply edits it out. It suppresses the visual input during the saccade and pastes in a smooth transition. It's editing your experience in real time, cutting out the parts it finds inconvenient. You are in a very literal sense blind for a significant portion of your waking life, and you have no idea because the editor in your head is that good. You can actually catch this happening, by the way. Go look in a mirror and look at your left eye, then look at your right eye. Then back at your left, you're making saccades, you're jumping from one eye to the other. But here's the strange thing. You never see your eyes move. Look as hard as you like. You will never see the movement. But if someone else watches you do it, they see your eyes darting back and forth clear as day. The reason you don't see it is that your brain is suppressing your visual input during each saccade. It's erasing the motion blur and replacing it with a stable image. The technical term is saccadic masking, and it's a vivid demonstration that your visual experience is not a live feed. It's an edited broadcast. And it gets worse, or better, depending on how you look at it. Right where the optic nerve exits the back of each eye, there are no photoreceptors. None at all. You have a blind spot in each eye, roughly the size of a lemon, at arm's length. A significant gap. You should notice it. You should see 2 dark holes in your visual field. But you don't, you never have. Because your brain quietly fills in those gaps. It looks at the surrounding pattern, makes an educated guess about what should be there, and paints it in. It's like a mason patching a hole in a wall. You see the patch, and it's so well done that you'd never know the hole was there unless someone pointed it out to you with a specific test. So let me ask you, if your brain is already fabricating resolution you don't have, editing out the blurry parts, painting over blind spots, stitching together jerky snapshots into smooth panoramas, do you really think it would be stumped by an upside-down image? The orientation of the raw input is one of the least interesting problems the visual system has to solve. It's trivial compared to everything else it's doing. But I haven't told you the best part yet because somebody actually tested this experimentally. A psychologist named George Stratton at the University of California in 1896 built himself a pair of goggles with inverting lenses. These lenses flipped the retinal image so that instead of being upside down as it normally is, the image on his retina was now right side up, which meant his conscious experience of the world was completely inverted. The sky was at his feet, the ground was above his head. When he reached right, his hand appeared to go left. But everything was backwards, reversed, chaotic. The first day was a disaster. He stumbled, he reached the wrong way for objects, he felt violently nauseous. His body and his eyes were in complete disagreement about which way was up, which way was down, where his limbs were relative to what he was seeing. For the first 2 or 3 days, it was essentially impossible to function normally. He describes in his journal the overwhelming disorientation, the frustration, the sense that the visual world had become hostile and untrustworthy. Even simple acts like pouring a glass of water became puzzles. He would tilt the pitcher the wrong way, his hand would move in the opposite direction from where he intended. He had to think consciously about every physical action that normally required no thought at all. Imagine having to relearn how to walk, how to eat, how to pick up a cup all at once as an adult. That's what Stratton endured. But here is the remarkable thing. He kept the goggles on, day after day. And gradually, slowly, his brain began to adjust. By the 4th and 5th day, movements were becoming more natural. He could reach for objects without consciously correcting. The world still looked strange, but it was becoming workable. By the end of about a week, something truly extraordinary happened. The world started to look normal again. Not perfectly normal, not 100%, but close enough to function. His brain had remapped. It had taken the new reversed input and learned a new set of associations. This signal now means that this pattern now corresponds to that location. The mapping was arbitrary all along, and the brain treated it as such. And then, when he removed the goggles, everything went haywire again. Briefly, for a few hours, the original, normal input felt wrong. His brain had to readapt to the mapping it had used for his entire life. But it readapted quickly, much faster than the original adaptation, as if the old mapping had been stored away somewhere, waiting to be reactivated. This experiment has been repeated and refined many times in the centuries since, with similar results. And what it tells us is something profound. The brain does not care about the absolute orientation of the retinal image. It genuinely does not care. It cares about relationships, correlations. When I move my hand this way, which signals change? When I step forward, what happens to the pattern? When I turn my head left, which way does the visual field shift? The brain builds its model of reality out of these dynamic relationships, not from the static orientation of a frozen image. The brain is, in this sense, like a telegraph operator who has learned Morse code. The operator doesn't care if the signal comes through a wire from the north or the south, if the transmitter is above sea level or below, if the electricity flows left to right or right to left. None of that matters. What matters is the pattern. ... means R, always. Regardless of which direction the current happens to be flowing, the code is the code, and the brain's visual processing works the same way. It reads the code, and the code is defined by relationships, not by raw orientation. This tells us something deep about what up even means. Up is not stamped on the retinal image. Up is not carried in the optic nerve signals. Up is a conclusion, a computation. The brain determines up by combining visual data with signals from the vestibular system in your inner ear, which detects gravity and acceleration. It cross-references with proprioception, your body's sense of its own position, which joints are bent, which muscles are contracted. It factors in memory, expectation, Context. Up is the output of a multisensory calculation, not an input from any single sense. This is why astronauts sometimes feel disoriented in freefall. The vestibular system is no longer getting a clear gravity signal, and without that anchor, the brain's model of up becomes unstable. The visual input hasn't changed, but the cross-referencing system has lost one of its key inputs and the model wobbles. And if you think about it, this is exactly what happened to you as a baby. When you were born, your eyes produced inverted images on your retina from day one, but you didn't know what any of it meant. You had no model yet, no associations, no mapping. Over weeks and months, your brain slowly learned to correlate. When it received a certain visual pattern and you moved your arm, certain signals changed. When your mother's face appeared, it was always associated with certain sounds and certain tactile sensations. Piece by piece, correlation by correlation, your brain built the mapping from scratch. It didn't need to flip anything, it just needed to learn which signals go with which experiences, and the fact that the retinal image was upside down was completely irrelevant to that learning process. If the image had been right side up or rotated 90 degrees or mirror reversed, the brain would have built its model just the same. The starting orientation simply doesn't matter when you're building from correlations. This is a profoundly important point, and I want to make sure it sinks in. The brain is not correcting an error. There is no error. An inverted image is not a mistake, it's just the way a lens works. The brain doesn't need to fix it because it was never broken. The brain's job is to build a useful model of the external world from whatever signals it receives, and it does that job regardless of how those signals are oriented or formatted or encoded. The format is arbitrary. The model is what matters. Let me push this idea further because I think it leads somewhere important that goes beyond just the upside-down image. Consider color. You look at a ripe tomato and you see red. That red feels like it's a property of the tomato, like it's out there on the surface, as real as the tomato's weight or shape, but it's not out there. Out there, there are electromagnetic waves with a wavelength of roughly 650 nanometers bouncing off the tomato's skin. Those waves are not red, they're not any color. Color is what your brain creates when those particular wavelengths hit certain cone cells in your retina. A honeybee looking at the same tomato sees something entirely different because its photoreceptors are sensitive to different wavelengths, including ultraviolet. A mantis shrimp with 16 types of color receptors compared to your 3 inhabits a visual world you literally cannot imagine. And a person who is colorblind lives in a slightly different visual world than you do. None of these models is wrong. None of them is the real color of the tomato. They're all models, constructed experiences, useful fictions built by different brains from different data. Sound works the same way. Out in the world, there are pressure waves in the air, compressions and rarefactions, molecules bumping into each other in patterns. These waves are not loud or soft, high or low. Loudness and pitch are things your brain invents when pressure waves vibrate your eardrum, and that mechanical vibration gets converted into electrical signals in the cochlea. The experience of hearing a symphony, with all its beauty and emotion, that's not in the air, it's in your head. The air is just carrying pressure fluctuations. Your brain is doing everything else, and smell, molecules drifting through the air land on receptors in your nasal cavity. The molecules are not fragrant, they're not pleasant or disgusting. Those are experiences your brain constructs from the chemical data. Everything about your sensory experience, everything is a construction. So the inverted retinal image is just one tiny example of a much bigger truth. You do not experience reality directly. You can't. What you experience is a model, a simulation, built in real time by about 86 billion neurons performing an almost inconceivable number of calculations, all running on roughly 20 watts of power, less than the light bulb in your refrigerator. And now, as a physicist, I find this both humbling and fascinating. Because in physics, we spend a lot of time talking about observation. We measure things, we observe particles, we observe fields, we observe wavelengths, and we like to think that our instruments are giving us the truth about nature. But every instrument ultimately has to interface with a human brain. And that brain is doing all this construction I've been describing. So there's a funny loop here. We use our constructed perception to design instruments that extend our perception, and then we interpret the instrument's output through the same constructive process. We never escape the model, we just refine it. This doesn't mean science is unreliable. Far from it. Science is reliable precisely because it doesn't trust any individual's perception. It demands that observations be repeatable, that predictions be testable, that multiple independent observers agree. Science is the system we invented to compensate for the fact that our perceptions are models, not direct access to reality. Every controlled experiment, every statistical test, every peer review is part of an elaborate error correction system designed to overcome exactly the kind of limitations I've been talking about. Now, I want to be honest about what we do and don't understand, because I think a physicist should always be clear about the boundaries of knowledge. And a teacher who pretends otherwise is doing you a disservice. We understand the optics very well. Lenses, refraction, image formation, that's all solid physics well understood for centuries. We understand a good deal about how photoreceptors transduce light into electrical signals. We know a lot about the early stages of neural processing, the edge detection, the motion detection, the contrast enhancement. The work that David Hubel and Torsten Wiesel did on the visual cortex, mapping out how neurons respond to edges at specific orientations. That was beautiful, precise science, and it earned them a Nobel Prize. We can trace the visual signals through various brain regions. The primary visual cortex at the back of your skull, which does the early processing, the ventral stream that runs down toward the temporal lobe and handles object recognition, telling you what something is, the dorsal stream that runs up toward the parietal lobe and handles spatial relationships, telling you where something is and how to interact with it. But the deep question, the really deep question, how does a pattern of neural firing become a conscious visual experience? How does electrochemistry become the redness of red? How does a cascade of voltage changes across membranes become the felt sense of seeing a face, or a sunset, or the color of your child's eyes? That question is still unanswered. Completely unanswered. It's called the hard problem of consciousness. And despite what you might hear from enthusiastic people at conferences, nobody has solved it. Not neuroscientists, not philosophers, not physicists. We don't even have a good framework for attacking it. And I think intellectual honesty demands that we say so plainly, rather than waving our hands and pretending the gap isn't there. But even without solving that deepest mystery, what we do understand is enough to demolish the naive picture of vision. The eye is not a camera. The brain is not a screen. Seeing is not passive reception. It is active, aggressive, creative construction. Your brain is not faithfully recording reality. It is authoring it. It takes fragmentary, noisy, ambiguous, inverted, gap-riddled data and produces from that mess a stable, coherent, three-dimensional experience so convincing that you have never once, in your entire life, suspected it was a fabrication. And that is the real story behind the upside-down image. So it's not about a lens and a flip. It's about the nature of perception itself. It's about the fact that every single thing you have ever seen has been a construction, built inside your skull, assembled from data that doesn't look anything like the experience it produces. The raw material is 130 million electrical pulses from an inverted, blurry, gap-filled retinal signal. The finished product is your entire visual world. Everything. Every sunrise. Every face. Every word. On every page. And this is why optical illusions work, by the way. An optical illusion isn't the failure of your eyes. Your eyes are reporting the light perfectly accurately. An illusion is a case where your brain's model-building process gets tripped up. The brain makes an assumption, usually one that works perfectly well in normal situations, and the illusion is designed to exploit that assumption. Two lines that are the same length look different because the brain is interpreting perspective cues. A static image appears to move because the brain is misreading contrast boundaries as motion signals. The illusion reveals the construction. It pulls back the curtain just for a moment and lets you see the machinery at work. And every time you fall for one, it's proof that you're not seeing reality. You're seeing a model, and sometimes the model gets it wrong. The next time somebody tells you your eyes see upside down but your brain flips the image, you can tell them, no, that's not what happens. By the time the brain gets involved, there's nothing to flip. The image is already gone, dissolved into code. What the brain does is not correct an error in orientation. It builds a world, a whole world, from scratch, every single moment of every single day. And it does this so well, so seamlessly, so silently, that the construction itself is invisible. You never catch it in the act, you just see the finished product and assume it was there all along. If that doesn't stop you in your tracks and make you sit quietly for a moment, appreciating the sheer improbability of your own experience, then I don't know what will. So here is my question for you. If everything you see is a model your brain built from incomplete, noisy, inverted data, How would you ever know if it got something wrong? Think about that for a while. Really sit with it. See what you come up with.